Hey everybody. All right, it's time to finish that life cycle. Um, we've talked about the middle life of stars on the main sequence. Talked about how stars start evolving off the main sequence and become red giants or red supergiants. We've talked about how they die, what they turn into after they die, white dwarfs, neutron stars, black holes. So it's time to loop back and talk about how stars are born, to get the entire life cycle completed. And the reason why I've saved the birth of stars to talk about last is because how stars are born is affected by how the previous generation of stars died. So you can't really get a good picture of why stars are born the way they are without looking at how stars die. So we'll see that here in a minute. Before we can talk exactly about how stars are born, we need to talk about what the material of stars are like before the stars are born. We need to talk about the gas that's floating around in the galaxy. So, for, well, most of the semester at this point, we've been focusing on stars, but there's more out there in the galaxy than just stars. Um, if you go out at night, it's best during the summer, but if you go out at night and look at the Milky Way is us looking into the disk of the galaxy. Our galaxy is kind of a disk shape, like a frisbee. And so when we look into the plane of the galaxy, you can see, well, there's a lot more stars in this direction because we're looking into the galaxy, as opposed to looking north of the galaxy or south of the galaxy, where you'd see fewer stars because you're looking outside of the disk. And so you see, well, what's giving off the light there? Stars. But there's also these dark areas, these dark lanes. And those dark lanes are gas and dust, right? Um, they are what's called the interstellar medium. The interstellar medium is just a fancy word for the gas and the dust that's floating out there in between the stars. Pardon me. Um, pardon me. Okay. Um, the interstellar medium is floating out there everywhere. There's just gas and dust that's floating out there in between the stars. But there are places in the galaxy where that gas starts to clump up and get thick and dense, and it absorbs the light from the stars behind it. So you'll look around the sky and there will be these dark areas. This is a dark blob here, or you could see these big dark veins going this way, where the gas and the dust has thickened up, it's condensed so that it becomes opaque. And so when you look in that area of the sky, it's black. Not because there's nothing in that direction, but it's black because the the gas and dust in the foreground is absorbing the light from the stars in the background. So what is the interstellar medium made of? What is this gas made of? Well, I think we've looked at this before, but this is a bit of a joke, kind of, to say, what are the important elements in astronomy? And what makes something an important element? Well, the most important element is hydrogen because it's the most abundant element in the universe. Stars are mostly made of hydrogen, and so is the interstellar medium. The second most abundant element is helium. So stars and the ISM, interstellar medium, are 3/4 hydrogen, 1/4 helium, and a little bit of everything else. And all of those, if you remember, all of those other elements in the periodic table, anything that is heavier than helium, we just lump it all together and call it metals. Because there's not that much of it, right? The metals are trace elements in the universe, in a universe that is overwhelmingly hydrogen and helium. But it turns out when you're looking around the interstellar medium, those metals become very important. So what is the ISM made of? Well, I've been saying for the last few minutes, the ISM is made of gas and dust. What do I mean? What kind of gas? Well, mostly hydrogen and helium. The dust is made of metals because those heavier elements, the carbon, the oxygen, the iron, the nickel, the silicon, the calcium, the mm, nitrogen, these metals, the heavy elements, these atoms are really good at sticking to each other and forming little granules. So as opposed to hydrogen and helium gas that are just gases made of one or two atoms, these dust grains are made of the heavy elements that stick to each other, and they form granules that are about a micron across. So what is a micron? A micron it's short for a micrometer, a millionth of a meter. Okay? These dust granules in the interstellar medium are about 100 atoms. They're made of like 100 atoms. So when I say dust, don't think about like the dust in your house, right? What's the dust in your house made of? It's made of um, dirt that blows in from outside, pollen grains, dead skin cells that slough off, bits of hair. Um, you know, these are huge, right? The dust grains in your house are huge compared to the dust in the interstellar medium. The dust in the ISM is microscopic. These are more like particles of smoke. That's how big they are. So interstellar dust is tiny compared to the dust in your house, but it's huge compared to the gas because the dust grains are made of 1 or 200 atoms, whereas the gas is made of 1 or 2 atoms. And what that means is that the dust is much, much better at blocking light. And preferentially, the interstellar dust is really good at absorbing short wavelength light. So I've got my little cartoon here, right? Let's say your dust granule is about this size. It's about 1 micron in size, which means it's really good at absorbing short wavelength light because the wavelength of the light is shorter than 1 micron, which means the odds are really good that that light is going to come in, run into the dust grain, and the dust grain will just absorb the light, like any rock absorbs light. Long wavelength light has an easier time just going around the dust grain, so that the interstellar dust preferentially absorbs blue light because it's shorter wavelength, and it lets the longer wavelength light, like the red and the infrared, pass right on through. That's why the ISM gets to be so opaque. It's not the gas. Even though the hydrogen and helium is 99% of the ISM, hydrogen and helium aren't that very good at absorbing light because this gas, remember how gases and light interact, right? The ISM is a thin, low density, cool gas. So the hydrogen and the helium only absorbs light at the specific wavelengths that it's allowed to absorb light at. It only absorbs its specific absorption spectrum. The gas does. The dust can absorb any wavelength as long as that photon runs into the dust grain and gets absorbed. But that preferentially happens with shorter wavelength light. So let's look at that blob of cool, cold gas that we were just looking at a minute ago. If you look at that in the blue light, all the blue light is getting absorbed. The green light, also getting absorbed. By the time you're starting to look in the near infrared, the edges of the cloud are starting to get thinner. The edges of the cloud are starting to become translucent, and you can actually see the stars in the background that you're not able to see as well over here. As you go to longer and longer and longer wavelengths, those long wavelengths light they're going around the dust grains so that they can pass right through the cloud for us to see here on Earth. This is how we know for sure. I said a minute ago, oh, if you look at this, it just looks like there's a hole in the sky, but it's not. It's just a dark cloud with the stars in the background. How do you know? Well, you know How do you know that there isn't just nothing in that direction? Well, you know because if you look at sufficiently long wavelengths, you can see through the cloud to see the stars far, far, far away. Um, in the last video, we were looking at the stars at the very center of the galaxy. Remember the stars that are orbiting around the supermassive black hole at the center of the galaxy? Those pictures were taken with an infrared telescope. Because when you look toward the center of the galaxy in visible light, there's a lot of dust in that direction that absorbs the visible light. You're not going to see those stars. But if you look in the infrared, you can see through the dust down toward the center of the galaxy so that you can watch those stars orbiting around the black hole. So if you want to see far away stars on the far side of the galaxy, you got to look in the infrared because the infrared can see through the ISM, whereas the visible light gets absorbed by the dust. Even though the dust is only 1% of the ISM, it's just so much more effective, it's so much more efficient at absorbing light that it's what makes the cloud dark. The dust is. So, okay. That's the ISM just floating around everywhere. How are stars born out of the ISM? Well, to figure that out, let's look at a place where stars are born, like, say, the Orion Nebula. Right? This may not look familiar, but those three stars there, that's Orion's belt. And if you look at Orion's belt and just look south, you'll see the glowing light from the Orion Nebula. The Orion Nebula is a star-forming region, but it's not the only one in the area. All of these nebula, that nebula, this one, big one over here, there's that little small one over there, this whole area, like basically this picture is the bottom half of the constellation Orion, and Orion is a big constellation. So this whole area, this whole big red bubble here, is what's called the Great Orion Molecular Cloud Complex. This is a whole group of nebulae out of which stars are being born. So if we zoom in on the Orion Nebula, what do we see? Well, we see a blob, a big cloud of gas, a nebula, right? It's what a cloud of gas is. It's what a nebula is. It's a cloud of gas. And we see all of these stars, and these are all newborn stars. These are stars that are recently born out of the gas. Right? And if you zoom in further to the Orion Nebula, you'll actually see some blobs of gas that are still in the process of forming. They're still in the process of turning in to newborn stars. So we can actually see the process of star birth happening, not exactly in real time because it takes a long time to fully happen, but we can see the process of stars that will eventually, or gas that will eventually become stars, gas that has already become stars, and the entire environment. And if we keep on zooming in, we can see more and more detail of the process here. Okay? So, that's the big picture. This is a different star-forming region. This is a picture of the Carina Nebula in the constellation Carina, hence the name, and this is another big star-forming region. And so this is a big nebula of gas, and all of these stars over here, and all these over here, and these ones over here, these are all fresh, young, newborn stars. And yet, if we zoom in, let's just zoom in on this part here, this is a blob, or several blobs of gas that are still coming together. Gravity is still pulling this gas together until it eventually evolves and turns into new stars. And so every one of these little knobs, every little rounded off bulb in this clump of gas is a mound of gas that gravity is still pulling together. The mass of that gas is exerting its gravity, pulling the gas together, and if you give it long enough, it'll eventually turn into stars. All right, so that's the short version. But let's look at this in some more detail. Before any of that happens, before there was the Orion Nebula, before there was the Carina Nebula, you started out with the interstellar medium, and it was very low density. The gas was very spread out, so it was very thin, and the gas was cold. Very cold. This is the important thing, because what does a hot gas want to do? What does a gas do when you heat it up? It expands. You don't want that. You want gravity to pull the gas into collapse, pull the gas together. So the gas has to start out 10 or 20 Kelvin. That's 10 or 20 degrees above absolute zero. If you've got this big spread out cloud of gas, like that dark nebula that we were looking at a minute ago, if the gas is cold enough, then those molecules are moving slowly enough that gravity can pull the molecules together and pull it into collapse. Then a few things happen. Eventually, well, to give you a decent idea here, the gas, as the gas starts to collapse, it clumps up. So the gas becomes clumpy and inhomogeneous, right? So that instead of just this cartoon here makes it look like, oh yeah, it's just the whole nebula just pulls in on itself, which happens for a little bit, but eventually the gas gets lumpy, and then the lumps start collapsing, and so you have a lump here, you've got all these lumps over here, this lump here, a few more over here and there, and then as the gas clumps up in clumps like this, then each of those clumps starts to collapse even more under gravity. And those are the smaller clumps are the ones that eventually collapse in on themselves and become stars. Then what happens, right? Remember when we were talking about energy? I know it's been a while, but I said before, the number one law of physics is the law of conservation of energy, that energy always has to be conserved. And so as that clump of gas collapses in on itself, you're taking a lot of gravitational potential energy, and then as the gas collapses, you're losing gravitational energy. Where does it go? That gravitational energy has to go somewhere. What does it turn into? It turns into heat. It turns into thermal energy. Because what happens to a gas as you compress it? Well, if you take the gas and it goes from being this big to being smaller, you're compressing the gas, it's going to heat up. So the gravitational energy turns into thermal energy, and that blob of gas warms up. What also happens is it starts spinning faster. We've talked about conservation of angular momentum in the context of neutron stars before, right? Pulsars, right? In a high mass star, when that iron core collapses down and turns into the neutron star, as that iron core gets smaller and smaller and smaller, the neutron star spins faster and faster and faster. The same thing is happening here, although not as ridiculous, not as extreme. But if you take that blob of gas, and if that blob of gas is rotating, which randomly it might be, no guarantee, but you got a blob of gas, there's a decent chance that it's got some slow spin to it. But as gravity pulls that blob of gas smaller and smaller and smaller, that blob of gas is going to start spinning faster and faster and faster. And then as that blob of gas spins faster, the random collisions between the molecules and the dust grains, and also centrifugal force, takes that blob of gas that probably starts out fairly spherical and has it turn into a flattened disk. As it spins faster and faster and faster, it flattens out into a disk. Okay? So, to recap here, right? You start off with a big, cold blob of gas, and it starts to collapse, and it gets warmer, it spins faster, and it flattens out into a disk. Okay? Most of the mass is going to collapse in toward the center. And so, as you take this blob of gas, and as gravity, as the mass of all that gas pulls itself together, and as that blob of gas gets smaller and smaller and smaller, it's going to get hotter and hotter and hotter until it becomes what you call a protostar. It's not a star yet. It's just a blob of gas that's collapsing and heating up. But it's starting to glow, right? This blob of gas, it becomes hot enough that it can start glowing with a decent amount of infrared light. So you tend to find these protostars, they're kind of reddish because they're cool, but really they're not giving off much visible light. They're mostly giving off infrared. And so if you look into a star forming region, um, like the Orion Nebula, if you look at it with an infrared telescope, you can see a bunch of hot blobs of gas buried inside the larger gas that tells you, oh yeah, there's a star in formation right now. Why do we think this happens? Why do we think this is how stars are born? And the answer is because we can see this happening in star forming regions like the Orion Nebula. When you look inside the Orion Nebula, here are the stars that are already born. But inside the Orion Nebula, you find a bunch of warm protostars. They're starting to glow with red and infrared light, and they've got a flattened out disk. I mean, here's a very flat disk of gas and dust orbiting around it. Okay? Most of the mass is falling in toward the center and becoming part of the protostar, but some of that gas and dust is going to be spinning and orbiting fast enough that it forms a disk around the protostar, and that's what we're seeing right here. All of these dark rings are the dust and the gas thickening up, becoming opaque, and orbiting around the protostar. And then here are some blobs of gas that are still in the process of collapsing and flattening out. So the fact that when you look in the Orion Nebula, in all these star-forming nebula, when you look at them, this is what stars during their formation process look like. Well, that must be what our sun looked like when it was getting born, too. You give this about 1,000,000 years, and this is a cartoon of what you end up with, right? Most of the mass has fallen in toward the center. The ball of gas at the center is collapsing down, heating up. Not a star yet, still a protostar. And all of this gas and dust out here has enough angular momentum. It has enough speed that it's just falling into orbit around the protostar. And this disk is the stuff that planets and moons and asteroids and comets all form out of, right? So that's a slightly different process. And if you want to know how planets are born, take Astronomy 111 in a future semester. We're going to focus on the star here because that's what the point of the class is. This happens for about 1,000,000 years. Eventually, that protostar collapses down and it heats up enough that it starts generating an intense little magnetic field. And so this protostar here starts making a magnetic field, and that magnetic field is able to grab onto the hot gas around it, and magnetic fields can exert forces onto charged particles. So if the magnetic field of the protostar grabs onto this hot gas, it exerts a force on it and sprays out that hot gas as two intense jets. One jet shooting out the North Pole and one jet shooting out the South Pole. Meanwhile, that protoplanetary disk of dust and gas is forming planets and asteroids and stuff. This is... If a protostar is a baby star, this jet phase is like the star's angsty teenage period. The star is reaching maturity. It's starting to heat up. It's starting to become a fully matured main sequence star, but it's not there yet. It's now starting to grow powerful enough that it can make a magnetic field, and it's starting to act out. And it's shooting out these hot jets out of the system, out of the disk. And again, we think this is how it works because we see this happening. Here's a bit of a movie made by the Hubble Space Telescope where you say, here's the disk, right? There's the protostar buried inside there, lighting up the disk from the inside, and then there's jets shooting out the two magnetic poles. And by shooting out those jets dump a bunch of angular momentum. It gets rid of speed from the gas, and when you slow down the gas, that gas then falls into the star, and the star is able to gobble up some more mass this way. It's able to accrete more gas. There's that word again. As the star starts to relax, as the star reaches maturity, that magnetic field relaxes, and so instead of shooting out those two intense jets like this, those jets widen out and slow down and turn into a hot wind that blows in all directions. And this is the last act of the protostar. That protostar blows this hot wind in all directions. It blows the rest of the gas out of the disk. And then when all the gas blows away, the only thing left orbiting the star is all the heavy stuff that formed in the meantime. By which I mean planets, moons, asteroids, comets, the big stuff that formed out of the disk while it had the chance. Then, after blowing out that wind, the star settles down. The star implodes not implodes, but the star collapses down one more time. Gravity pulls the mass of the protostar in until the core reaches that magic number. There's 10 million Kelvin, and as soon as the core of the star reaches 10 million Kelvin, the hydrogen in the core can start fusing. The hydrogen fusion starts. The star can now generate its own heat, and then the star starts to shine. And now you've got a fully matured, hydrogen-burning main sequence star. And the star will stay that way for as long as there's hydrogen in the core to burn. You've got a star now. Right? So if you're watching stars being born on the HR diagram, this is what it looks like. You start off with, well, the gas starts out way off the HR diagram because it's not nearly hot enough, but then as that blob of gas collapses down and gets smaller and smaller and hotter, eventually it starts emitting some red light. And these protostars, the protostars over here, are actually pretty bright. They're pretty high luminosity, not because it's hot, it's not, but because it's so big. That blob of gas is still shrinking and heating up. And so as that protostar shrinks and heats up, it gets hotter and therefore bluer, but also lower luminosity, until finally it shrinks down one last time, it crunches down, the core reaches fusion temperatures, and it lands on the main sequence based on whatever mass it has. Because remember, mass is destiny. This is the birth track for a star like the sun, right? A star like the sun will land here as a yellow star at about 6,000 Kelvin and 1 solar luminosity, because that's what a star has to be. This is the temperature and the luminosity that establishes hydrostatic equilibrium between gravity and pressure for a star of that mass. If your star is lower mass, if that blob of gas has less mass, then it kind of comes up here and then it just settles onto the main sequence over here, and there you go. If the star is higher mass, then it starts out bigger and hotter, and then it gets hotter and hotter and hotter and hotter until it finally settles into the main sequence somewhere on the blue end of the main sequence, right? Where a star is on the main sequence, and everything that happens after that, from main sequence to death, is dictated by how much mass did that protostar accrete. How much mass did that blob of gas have that the star was born out of during this whole phase? The destiny of this star is imprinted, is determined by the size of that blob of gas from the very beginning. That mass, that birth mass, runs out at some point, right? Either the protostar just sucks up all the gas that it has around, or the jets in the wind blow the rest of the gas away. And if that protostar blows the rest of the gas away, then that gas can't be accreted by the star. The star is only born with whatever mass it's born with. I mean, that really is the determinant here. That protostar will have that mass. That protostar will have the mass that it can grab and pull in and accrete until it shoots out that wind, and once it blows out that wind, the rest of the gas around it blows away, and the star has however much mass it has. And that's the mass that will determine where it lays in the main sequence and where it goes after that for, well, unless something more complicated happens, like in the case of close binaries or something. But that's, for a simple solitary star like the sun, that's the story. That's how a star is born. There's a little bit of randomness here, though. This is where things get really interesting. Because remember what I said. It's not like you have a big blob of gas and then the whole thing just implodes and forms a star. That was kind of the old picture. If you were studying astronomy 60, 70 years ago, that's what people thought. People thought you have a blob of gas, it collapses under gravity, and then at the center here will be a star. Today we know better. Today we know that's not what happens. Why? Because gases don't just implode. Gases also move in random directions. And so this is a simulation that you sort of throw all the physics that you can think of into a computer and say, what would happen? Okay? So here's a simulation of what star formation looks like. You got this big blob of gas. It's pretty low density, right? So the redder it is, the lower density, the whiter it is, the higher density. This simulation was made to simulate how stars are born. Let's see what happens. So instantly, because those gas molecules are moving in random directions, that gas instantly starts to clump up. And then each of the clumps has mass and it's able to pull in the gas around it. So you've got these random motions of the stars pulling on of the gas pulling on each other, and now we're going to rescale our image and let it keep on going. Let this gas swirl around. Okay, we're rotating the simulation to get a better view of that yellow area. We're zooming in. All right, so pause here for a second. I'm going to pause. Don't you pause. So these yellow blotches here are the heaviest lumps. These are the densest lumps. And so that's the densest part is where gravity is going to be the strongest. The gravity pulls the gas inward and it forms stars. And this simulation is programmed so that when a star is born, that star is tagged as a white dot. So when you start seeing white dots show up, those are stars that are born. And now there you go, right? Out of this clump of gas, you've got all this gas falling inward, swirling together, and stars are being born. It's kind of chaotic because now you've got these stars, they're pulling on each other and whipping around each other. It's not sort of the nice, quiet story that I just told you. It's chaos, right? Look at this giant blob of gas here, and this blob of gas is so massive, it's now going to pull in all of this gas around it, and as that gas falls inward, stars are born, and those stars are just getting whipped around and shot out. And they just go flying, right? All over the place. So now, if we let the simulation go for a while, and now we're sort of at the end here, and we're going to rotate. Now you've let time go, and there are now stars all over the place. What did you notice? What did you notice here? I'm going to go back here and play this from when the stars started here. Here we just got gas. Stars are starting to form. All right. Take a guess as to how massive that star there, the one that's pulling everything in, how massive is that star? It's got to be really massive. But that star that just shot out there, right? Some of these stars are getting really easy to shoot out. How massive are those stars? Not very, right? The stars that are really easy to throw around and chuck out, those must be really low mass stars. And yet here you got this one star here that must be absolutely huge because it's able to pull in gas, and then as this gas spirals in, it's giving birth to other stars that are then being thrown out of the system. so that you can, if we play this, if we yeah, in here, right, in the centers, you got these really high mass stars that all the gas and other stars are orbiting around. Meanwhile, all these little stars, I mean, do we know they're little? I know they're just white dots in the simulation. But these are the stars that are being thrown out by the random whipping around of gas. Right? Um, this gives you an example of what's called the initial mass function. All right, this graph looks complicated, and it kind of is, so let me simplify it here for you. When stars are born, you never find stars that are all the same type. When stars are born in places like this, when stars are born in nebula, you never find all low mass stars or all high mass stars. What you always find is a mixture. When stars are born in these star forming regions, there's a mixture of high mass stars and low mass stars, but it's always like this. This initial mass function is basically a graph of the number of stars that are born on the vertical axis and the mass of those stars on the horizontal axis. So when stars are born, you always get a few high mass stars, more medium mass stars, and lots of low mass stars. In fact, the most common stars that are born are the low mass stars. Always. For reasons, and this is still kind of a big question mark in astrophysics, right? Why? All of these different lines here, all these different curves are different models, essentially, for how stars are being born. And they all agree, all these lines line up, they all agree around here. It's when you get to the really low mass end that the models sort of get shaggy and disagree. Why is that? Well, because, like you just saw in the simulation, the high mass stars are the first ones. Right? It's easy to form a high mass star. All you need is a lot of mass. You just need a lot of gas. Those get born first. Then you get a medium number of medium mass stars, and you get a lot of low mass stars. How many low mass stars? Is it this many low mass stars, or does it sort of flatline at some point? This is a question that people are still trying to figure out. Does the number of low mass stars just keep on going upward and upward and upward forever? Maybe not. But maybe the number of low mass stars sort of peters out at some point. This green line here, I don't know. I think the idea that it just sort of stops at some point seems dubious. But a lot of these models here are basically saying the formation of low mass stars kind of peters out at some point. Fundamentally, the same relationship holds, though, right? There is a relationship between the number of stars that are born, the vertical axis, and the mass. The higher the mass, the fewer stars are born. The lower the mass, the more stars are born. For example, this is a picture of the Pleiades cluster. Right? This is a young cluster of stars. These stars are only a few million years old. So these are still young stars. The colloquial name for the Pleiades star cluster is called the Seven Sisters. Are there 7 stars in this cluster? No, look at that. There's clearly more than 7. There's actually a few hundred stars in this cluster. So why is it called the Seven Sisters? And the answer is because you can only see the 7 brightest with the naked eye, right? 1, 2, 3, 4, 5, 6, 7. You can only see the 7 brightest, the 7 highest luminosity, with the naked eye. Why? Because those highest luminosity stars, why are they high luminosity? Because they're high mass. And high mass is the rarest kind of star. So you can only see the 7 highest mass, highest luminosity stars. The other several hundred stars are the most numerous. Why are they the most numerous? Because they're the less massive, and if they're less massive, they're also less luminosity, and also a fainter apparent magnitude. So you can't see them with the naked eye, but with a decent camera like this, you can see a lot of them. Right? So why? Well, there's two big questions here. There are some questions about the most massive stars, and there are some questions about the low mass stars. Well, why do we think that? Why do we think that maybe the low mass stars keep going up, or do they sort of does this line bend over at some point? Um, and the answer all has to do with the highest mass stars. What is the well? To go back a second, um, there's no question about what the lowest mass star can be, because the lowest mass that a star can be born with is about 8% the mass of the sun. Because if you have a blob of hydrogen, if you have a ball of hydrogen less than 8% the mass of the sun, the core will never reach 10 million Kelvin, hydrogen fusion will never start, it won't be a star. What's the highest mass that a star can be? Well, that's difficult, because as a star gets more and more and more massive, it also becomes higher and higher luminosity. And at that point, once the star gets ridiculously high luminosity, it can actually boil some of its own mass away. For example, here's again the Carina Nebula. That star right there is named Eta Carini. Eta Carini is one of the highest mass stars in the galaxy. If you zoomed in, here's what it looks like. You can actually kind of make it out there. This the sort of the blob of gas there. What you're looking at is there's the star, but this star is so high mass, so high luminosity, the outer layers of the star's surface are blowing away. That's how much energy is pushing away from this star all the time. So this is why there's a maximum mass that a star can be, because if I just added even more mass onto this star, it would just blow right back, and the mass would not have increased. So at some point, you just make a star that's so high mass, any more that you pack on there immediately blows away, and that's it. That's as big as you can make them. What is that mass? What is that maximum mass that a star can be born with? Depending on how you do the math, depending on how you make the predictions, usually the answer is something like 100 to 150 solar masses. What's the mass of Eta Carini? It's probably on that upper end. It's probably something like 120 or 150 solar masses. So big and very, very bright. These high mass stars, which you just call the O and B stars, right? O and B spectral type. What are O and B stars, right? They're the hottest, the brightest, the bluest stars. Why are they the hottest and the brightest and the bluest? Because they're the highest mass. So because those stars are high mass, they're the ones that are born first. When that happens, when the O and the B stars are born, they start giving off a lot of light, they start giving off a lot of heat, and they can light up all the gas around them. So this is one of the reasons why star-forming regions look like this. Why is all this swirling gas here glowing? All this gas is glowing because it's being heated up. What's heating it up? The O and B stars, right? Those O and B type stars, like Eta Carini, like these high mass stars over here, those two there, those three over there. Those O and B type stars are so high luminosity, they're giving off so much light that they light up the gas around them and make the whole nebula glow. And remember, the high mass stars are also the rarest, so that it doesn't take that many. In this whole nebula, there are only a handful of O and B type stars that are being born, and yet those O and B type stars are so hot and so bright, they light up the entire nebula. They light it up, and, what kind of gas is most of the nebula made of? It's mostly made of hydrogen. So these star-forming regions are another name for these star forming regions are called H2 regions. H2 basically is astronomer code for hot hydrogen. So the H meaning hydrogen, and 2 meaning it's hot, as opposed to H1, which is cold. Is it more complicated than that? A little bit, but I don't want to get into it. So, so an H2 region is basically a region of hot glowing hydrogen. Why is it so hot? Because those O and B stars that just got born are heating up the gas and making it glow. So the Orion Nebula is one of these H2 regions. All right. Here is both of these, the Orion Nebula and the Eagle Nebula, are stellar nurseries. They're star-forming regions. They're H2 regions. And they're mostly, what, two colors? Well, the Eagle Nebula is mostly red. The Orion Nebula is red and blue. These two pictures are pretty close to what the nebulas would look like with the naked eye. So those are true color images if your eyes could see that well. So what's glowing red? It's the hydrogen, right? Remember, hydrogen has a bright red emission line, and so when you heat up hydrogen, it glows, and it's going to glow mostly with that one specific red color at 656 nanometers. Where's the blue light coming from? It's coming from the O and B stars. All of these O and B stars over here, these O and B stars here, the ones that are inside the nebula, they're giving off, they're hot, so they're blue, and that blue light comes off the star, bounces off the nebula, and then shines on the Earth, so that we're seeing the blue starlight reflect off the gas, and then we're seeing the red light of the gas giving off its own light too. Here are a few other H2 regions around the galaxy. So the North American Nebula, the Lagoon Nebula, the Horsehead Nebula. The Horsehead Nebula is also in the Orion molecular cloud complex. So we were looking at that at the beginning of the lecture. Whenever you see a big, red, blotchy, glowing object, you go, aha, stars are being born in there. Because it's those newborn stars that are lighting up the hydrogen, making it glow. So the next thing we're going to talk about, and something we're going to talk about for the rest of the semester, is galaxies. So if we zoom out, or not zoom out, but if we look into another galaxy, this is the galaxy M51. When you look in M51, it is studded with red blotches, right? All over the big ones like this one, the medium-sized ones, these small ones. Every red smudge, every red blotch in this image, why would it glow red? It's an H2 region. So when you start looking at other galaxies, the smoking gun, the telltale sign is look for the red blob, look for the red blotch. And you see these giant ones over here. Holy mackerel. But when you start looking in our galaxy, when you look around our galaxy, and when you look into other galaxies, if you see a red glowing blotchy region, you go, there are stars being born in there right now, and they're giving off, or those small number of O and B stars are giving off so much light that they heat up all that hydrogen and make it glow red. That's how you know. That's how you can tell. Meanwhile, right, remember what I said, the high mass stars, the O and B stars, they form first. What happens to all the rest of the stars, though? What about the medium mass stars and the low mass stars? This becomes a little more complicated, because we've got a problem, right? These, okay, give you a better idea here, or even better, Carina Nebula, gorgeous, right? The gas is glowing. Why is the gas glowing? Because it's hot. What does a hot gas want to do? A hot gas wants to expand. And if this gas is all expanding, then it's not collapsing. But you need the gas to collapse in order to give birth to stars. So these stars are already born, right? All the stars that you're seeing right now, those stars are already born. Their main sequence, they're good to go. But all of these blobs of gas, the ones we zoomed in on, that one, and this big thing over here, there are stars still trying to be born that might not get the chance because all the gas that they're being made out of is being heated up and evaporated by the O and B stars that are already born right now. Here's a great example. This is the famous pillars of gas in the Eagle Nebula. Here's the true color image, right? Here's what the Eagle Nebula looks like to the naked eye, mostly red. Here's those pillars of gas right there, and here's a cluster of O and B stars right above it, right above the pillars. This picture here is usually the more famous one. This is not true to the naked eye. This is a color code, and I want to say the red color is like sulfur emission, and the blue is probably oxygen emission, and the yellow is helium or carbon or something like that. So this is a false color image, but it gives you it lets you see in a lot of detail, and it gives you an idea about what's going on, because up above here, up above these pillars, you've got all these O and B stars giving off hot radiation, and it's heating up the gas, and you can actually see the gas evaporating. See how this gas gets all wispy as it's coming off the pillar. So inside here, all these little nubs that the arrows are pointing at, all the little tentacles that the arrows are pointing at, each of those little nubs is a dense clump of gas that gravity is trying to collapse inward to give birth to a star. There's a ticking clock here, right? These stars are racing against time. Can each of these blobs of gas collapse down and heat up enough to become a main sequence star? Or will those O and B stars evaporate all the gas, and if the gas evaporates away, then you can't give birth to stars out of it? Those O and B stars could kill star formation by evaporating all the gas. Is this important? That is a decent question, right? Because, like you saw from the previous simulation, this is complicated. There's a lot going on. There's a lot of moving parts here. So, is this radiation being given off by the O and B stars? Is this really that important? Does it really affect the stars that are born? Or is it just a cute curiosity? Let's try. Okay, so here are two identical simulations done by Jim Dale and Clark and Bonnell a few years ago. All right, the one on the left is just going to be gravity and angular momentum pulling gas together to form stars. The one on the right is going to throw in that hot radiation being given off by the high mass stars after they form. Let's see what happens. All right, looking the same so far. Okay, stars are being born. Aha! So now these hot, high mass stars are eroding the gas. They're evaporating the gas, blowing the gas away. And we didn't turn that on. We turned off, in the simulation on the left, we turned that off. So that's not an important deal here. Okay. Which simulation gave birth to more stars? Which simulation has more white dots? The one on the left does, right? Because you didn't account for the radiation of those O stars blowing the gas away, that meant there was plenty of gas floating around here to give birth to more stars. Okay, now which simulation looks more realistic? Which simulation actually looks like actual star forming regions? You need the radiation, right? The reason why this nebula and this nebula look so hollow on the inside, the reason why they've been hollowed out is because those O and B stars eroded away all the gas on the inside, leaving a cavity. That's why the inside of the Orion Nebula looks empty like that. So apparently you have to account for this ionizing radiation. Apparently you have to account for the O and B stars and their radiation in order to explain why star-forming nebula look the way that they do. The downside of that is that kills the formation of stars. There are stars here that were never born because the gas blew away. There's one more thing. Because, well, to go back here, so there's some high mass stars in here, right, eroding away all this gas. What else do we know about high mass stars? How long do they live? The highest mass stars only live for a few million years. Well, a few million years is exactly how much time was in this simulation, right? 7.58 mega years, million years. These simulations, right, the star formation out of the gas, takes a few million years to happen. And that's exactly the timetable for those O stars to be born. Those stars, those high mass stars, will be born, they'll live their entire lifetimes, and they die over the course of this simulation. And what happens to a high mass star when it dies? It explodes. It goes supernova. These high mass stars, these highest of the high mass stars, the O stars, they are born, they live their entire life in the nebula that they were born in, and then they die. They never leave. They never leave the star forming region. So what happens then? Well, here's another simulation where we got a cloud of gas. Building a star and then having it blow up is more complicated than we need for this simulation. So basically they made a blob of gas and they just said, okay, we're going to magically put a star there and then blow it up and see what happens. So there's the shock wave, right? That supernova explodes, and that explosion sends a shock wave outward into the rest of the gas of the nebula. So what's happening? The explosion slams into the gas, causes the gas to clump up and condense. Well, when the gas condenses and clumps up, what's going to happen? Gravity's going to do its thing. Gravity is going to take those clumps and pull them inward and cause the gas to collapse and give birth to new stars. So if we, somewhere here, eventually this gas is going to thicken up and clump up enough. There it goes. The white dots. There are new stars. There are stars that were born out of this gas because the supernova blew it up, because the supernova blew up the star. This star in the center there exploded, and the shock wave slammed into all the gas around it, caused that gas to condense, and then gravity pulled that density of gas into collapse and gave birth to a whole bunch of new stars that weren't there before. So, do high mass stars kill star formation, or do they cause more star formation? The answer is probably both. That in order to understand the stars that we have, in order to understand the stars that are born, we kind of have to play the game both ways and say the shock wave caused by supernova explosions will trigger new stars to be born, but at the same time, the radiation and the luminosity of the high mass stars also evaporates the gas and blows it away and halts star formation. The answer is both. This is why the initial mass function is so complicated. This is why the different models for the initial mass function don't agree at the low mass end, because it's a race against time. You know, those lumps of gas are trying to collapse. They're trying to pull inward. They're trying to give birth to low mass stars. And the question is, well, will those stars be created by supernova? Or will those low mass stars be killed because the gas blows away from the radiation? And reasonable minds can disagree, which is why those graphs get so divergent at the low mass end. Something about all of this stuff, all of these different effects, gravity, motion, the evolution of stars, ionizing radiation, supernovas, you throw all of it together, and there's something about the way all those forces play off each other that recreates the initial mass function everywhere in the universe. You always, always, always find a small number of high mass stars and a large number of low mass stars. Everywhere in the universe, every population of stars you see in the universe is like this. The exact details, are a work in progress, but the basic physics are pretty simple. So that's what we've just gone over. All right. Next thing we're going to do is to go back to galaxies here. So this kind of concludes our conversation about individual stars. We've seen how stars are born out of the interstellar medium. We've seen how stars live their lives on the main sequence, how they transform as they leave the main sequence, and then how they die, and then what kind of corpses they leave behind after they die. We've seen the entire life cycle of stars from birth to death, and this is why I said at the very beginning, the deaths of stars affect the next generation of stars. The only way to explain star forming regions that we see, the only way to explain the star forming regions that we see, we need to understand the lives of those O and B stars. And also, in order to understand the stars that we do see, we need to understand how stars die. A star had to die to give birth to all of these other stars. Does this happen in real life? Almost certainly. And so, how stars live and die affects the next generation of stars that are born right around it. The next thing we're going to do is zoom out and start looking at the whole galaxy. We're going to look at the Milky Way galaxy, our home galaxy, and then we're going to zoom out some more and start looking at all these other galaxies in the universe to say, what else can we figure out about them? What are they like? Why do they look the way that they look? How do they work? Because once you've zoomed out far enough, galaxies become the building blocks of the universe. So if we're going to understand the whole universe, we need to zoom out and not just look at individual stars. We need to look at entire groups of stars by the billions that make up galaxies. So, but galaxies are made of what? They're made of stars, the glowing stuff, and they're made of dust and gas, the interstellar medium. And so if we understand how gas and stars work, we can get a pretty good handle on how all galaxies work. And that gives us a huge advantage in figuring out about the whole universe. Capital E, everything. So this is going to take us through the end of the semester. All right. Thanks a lot, guys. I hope you're doing well. See you next time.